Good day everyone, we are Group 7 and today we are pleased to present our project for Introduction to Mathematical Economics. In this presentation, we will walking you through our analysis and the mathematical solution for our assigned question. On this slide, you can see the members of our team who contributed in this project. We are now ready to present our work to you. Let's begin.
Question 1a. Consider the function y equal to fx equal to 2x power of 3 minus 9x power of 2 plus 12x minus 4. Find the interval where f is increasing and decreasing. Be sure to construct the sign diagram to support your conclusion. Question 1. So the first step is we need to differentiate the function and it will become 6x power of 2 minus 8x plus 12. Next, we need to factorize it and we will find x power of 2 minus 3x plus 2. And lastly, we will factorize again and we will find x minus 2 and x minus 1. So the critical point are x equal to 1 and x equal to 2. So next, we will find three intervals. First of all is negative infinity to 1. Next is 1 to 2. Next is 2 to infinity. So for the first one, we will use test value of 0. Next is 1.5 and next is 3. So using a side diagram, we will find that the function is increasing when s is less than 1, decreasing between s equal to 1 and x equal to 2, and increasing again for s more than 2. Therefore, the function is increasing on negative infinity to 1 and 2 to infinity and decreasing on 1 to 2.
Now, let's apply this to an economic context in question 1 part B. A firm has a demand function where PQ equal to 100 minus 4Q. To derive the total revenue, we use the formula R equals P times Q. Substituting the demand function, we get RQ equals 100Q minus 4Q squared. We also check the concavity by finding the second derivative. R double prime Q equals to negative 8. Since negative 8 is less than 0, the function is concave downward, which is typical for revenue functions, indicating there is a single clear peak or maximum point. Continuing with the revenue function, we need to find the specific output level that maximizes it. We set the marginal revenue, which is R prime Q equals 100 minus 8Q to 0. Solving this gives us Q equals 12.5 units. Economically, this means the firm reaches its peak revenue when it produces exactly 12.5 units. Producing any more or less will result in lower total revenue.
Now, let's look at question 2, part A. We are given a total cost equation which is TC equal to 100 plus 2Q plus 0.1Q square. In this formula, TC represents the total cost of production, while Q represents the specific number of units produced. For the first question here, our goal is to calculate the marginal cost or MC. To find this, we need to take the first derivative of our total cost function. Let's break down the derivative of our equation. Derivative of the constant 100 is 0. Derivative of 2q is simply 2. And for the 0.1q square, we apply the power rule, multiplying the exponent by the coefficient, which gives us 0.2q. When we put it all together, we find the marginal cost for the company is MC equal to 2 plus 0.2q. Now that we have our marginal cost equation, the next step is to determine if this cost will increase or decrease as production level rise. Looking back at our result, MC equal to 2 plus 0.2q, we focus specifically on the relationship between marginal cost and the quantity. You will notice that the coefficient of Q is positive 0.2. This means that as the quantity produced increase, the marginal cost also increase.
For question 2b, I will answer directly. So for question 2b, we are given the price function P equal to 100 exponent power of negative 0.05q. The question asks us to find the quantity, the maximum total revenue, and to determine the interval where total revenue is increasing and decreasing. First, total revenue is found by multiplying price and quantity. So total revenue equal to 100Q exponent power of negative 0.05Q. To maximize total revenue, we differentiate the revenue function with respect to Q. This given 100 exponent power of negative 0.05Q times 1 minus 0.05Q. We set the derivative equal to 0. Since the exponential term is always positive, we solve 1 minus 0.05Q equal to 0, which gives Q equal to 20. This means total revenue is maximized when 20 units are sold. When Q is less than 20, total revenue is increasing, and when Q is greater than 20, total revenue is decreasing.
Next, determine if the marginal cost is increasing or decreasing as production increase. This table is used to determine whether the function is increasing or decreasing by analyzing the sign of the first derivative. First, the critical point is at x equal to 20. This value divides the domain into two intervals, which is from negative infinity to 20 and from 20 to positive infinity. A test value of 10 is chosen from this interval. When 10 is substituted into the first derivative, the result is positive, which is approximately 30.33. Since the first derivative is positive, this means the function is increasing on this interval. Next, a test value of 30 is chosen from this interval. When 30 is substituted into the first derivative, the result is negative, which is approximately negative 11.16. Since the first derivative is negative, this means the function is decreasing on this interval. So, since the first derivative changed from positive to negative at x equals 20, the function has a maximum point at x equals 20.
So we move to question 3. Question 3 considers a local manufacturing company that aims to maximize its profit. The company is given a demand function where Q minus 90 plus 2P equals 0 and an average cost function AC equals Q square minus 8Q plus 57 plus 2 over Q. So we look at question 1 Roman. The objective of this question is to find the value of output Q that maximizes profit. To begin, we first derive the total cost function by multiplying the average cost by output Q. This gives the total cost function as Q cubed minus 8Q squared plus 57Q plus 2. From the demand function, we rearrange the equation to obtain the price function, where P equals 45 minus 1 half Q. Using this price function, total revenue is calculated as price multiplied by quantity, resulting in 45Q minus 1 half Q squared. Next, we find the profit function by subtracting total cost from total revenue. This gives P equals minus Q cubed plus 7.5Q squared minus 12Q minus 2. To maximize profit, we take the first derivative of the profit function and set it equal to 0. This gives the critical point at Q equals 4 and Q equals 1. So we look at question 2 Roman. The objective of this question is to determine which value of Q yields maximum profit using second order condition. At Q equals 4, the second derivative is minus 9. Since this value is negative, it confirms that the profit function is concave downward at this point. Therefore, Q equals 4 is the output level that maximizes profit.